We are now going to be taking a look at what is called the rational root theorem. We use this when a polynomial function cannot be factored. And we've learned before in the quadratics unit that not all quadratics were factorable. We had to use completing the square or the quadratic formula. Here, when something is not factorable, we're going to have to use synthetic division. Now, synthetic division, remember, normally we have a list of our coefficients in the first row, and then we have to have some number on the outside. To get that number on the outside, normally what we did is we set our divisor equal to 0. Well, we don't have a divisor because it's not factored yet. So we need to have numbers to test and see which ones would work. And the way we get that list of numbers is using the rational root theorem. So I'm going to put a plus or minus out front because I forgot to put that in there. It would actually be plus or minus all of the factors of the constant term over all of the factors of the leading coefficient. So if I'm looking at example 1, I'm going to have to list out, so use plus or minus, all of the factors of my constant, which is the number 24 in this case, over all of the factors of my leading coefficient. Remember, the leading coefficient is the number in front of the term with the highest power. So if it wasn't already written in standard form, you should probably do that before beginning this process. The factors of 24 are 1 and 24, 2 and 12, 3 and 8, 4 and 6. The factors of 1 are just 1 times 1, right? So if I'm going to list them out, it's going to be plus or minus all of the factors of the constant. So these are going to go in the numerator, all of these factors, plus or minus 1, I have plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24, all over all of the factors of the leading coefficient. So plus or minus, in this case, there's only really one factor, which is 1, which is really, really nice, okay? When we have a leading coefficient of 1, that basically just means I have 1 over 1, which is 1, 2 over 1, which is 2, 3 over 1, which is 3, so on and so forth. If this would have been like a 2, let's say, the factors would have been 1 and 2, so I'd have plus or minus 1 here, plus or minus 2 here. That means I would have to put all of these factors over 1, and then all of these factors over 2. So that makes it a lot more numbers we have to test. All right, so let's take a look at part B. It says test the possible roots to find which one is an actual root. So all of these are my possible roots, and if we wanted to, we could even simplify it just as plus or minus 1, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 12, plus or minus 24. Okay? How do I know if one of these is an actual root? Well, you might remember from our 3.4 notes, we discussed that something is a factor or a root if, using synthetic division, we find out that the remainder is equal to 0. So the way we have to test this is using synthetic division. Let's say I want to test a positive 1. 1 would go on the outside, and I would use synthetic division. Looking at my equation, it's written in standard form, and I do not need any placeholders. So I'll put 1, 3, negative 10, negative 24. Let's see if we get a remainder of 0. Bringing down the 1, 1 times 1 is 1, 3 plus 1 is 4, 4 times 1 is 4, negative 10 plus 4 is negative 6, negative 6 times 1 is negative 6, and then the remainder would be negative 30. So is this a factor? No, it is not. Well, we just got to pick another one and test it out. I've already tried a positive one, but remember this is plus or minus, so another possible root is a negative 1. Let's see if that works. 1, 3, negative 10, negative 24. Okay. Bring down the 1. 1 times negative 1 is negative 1. Negative 3 plus, positive 3 plus a negative 1 is a positive 2. 2 times negative 1 is negative 2. Add those together, I get negative 12. Multiply by negative 1, I get positive 12. The remainder is negative 12. So that doesn't work either. Okay, let's try another one. So I have a plus or minus 2 next. Let's just try a negative 2. All right, 1, 3, negative 10, negative 24. Bring down the 1. 1 times negative 2 is a negative 2. 3 plus negative 2 is 1. 1 times negative 2 is negative 2. Add those together, I get negative 12. Multiply by negative 2, I get a positive 24. And I do have a remainder of 0. So negative 2 is a factor. But if I'm factoring it, I would need to write my minus 2 as a binomial, which would be x plus 2. Because if I have x plus 2 equal to 0, that would give me my negative 2 as a solution. So once again, that negative 2 needs to be written as a binomial. And then in parentheses, I would write my new quotient. We started with an x cubed, so now I know this is x squared. I have 1x squared plus 1x minus 12 equals 0. All right, now we do want to factor the polynomial. I've already gotten it down to a quadratic now that I've used synthetic division. So I can just use guess and check here. Because this is x squared, it's x times x. And then what multiplies to give me a negative 12, but adds to give me a positive 1. Well, because it's a negative 12, I know it's plus or minus, and to get to a positive 1, I would have to have a positive 4 and a negative 3. I know it doesn't ask for it, but let's just go ahead and list out our zeros then. We have negative 2, which we found, remember, a negative 4, and a positive 3. So negative 2 was just the solution that I found first. Had I tested a positive 3 or negative 4, my work would look a little bit different, but we would end up with the same answers. Example 2, the first thing we have to do is using this equation, determine how many possible x-intercepts we have. Well, how many actual x-intercepts we'll have is dependent upon the multiplicity. So I can't just say I know exactly for sure, but looking at the degree, remember the degree tells us how many zeros we have. So we can have up to 3 x-intercepts because there are 3 zeros. All right, now we need to know, well, what are those zeros? In order to find out what those zeros would be, we have to use the rational root theorem. P would be the constant, so that 12. That negative doesn't really matter because we have plus or minus anyway. So I'm just looking at the 12. And then Q is the leading coefficient, which is 1 in this case. Remember, that's nice. So I can just rewrite it as plus or minus the factors of 12. So that's 1 and 12. 2 and 6, 3 and 4. Now I went ahead and just wrote them as whole numbers because technically it's all over plus or minus 1, but that doesn't impact anything at all. So I'm just going to leave it like this. Now, are all of these possibilities really going to be solutions to the function? No way. We have to test them and see which ones do work. So let's just do, really, you can pick any number you wanted. I like to start with the smaller numbers because the math is a little bit nicer. So I'm just going to test 1. Checking for placeholders and if it's in standard form. Yes, it is in standard form. I have no placeholders, so I can just go ahead and put 1, 3, -4, and -12. All right, starting synthetic division, bring down the 1. 1 times 1 is 1. 3 plus 1 is 4. 4 times 1 is 4. -4 plus 4 is 0. 0 times 1 is 0. Well, I have a remainder of -12. So, no, that does not work. Let's just try, because it was plus or minus, I've tried the positive. Let's try the negative now. So 1, 3, -4, -12. Starting synthetic division, bring down the 1. 1 times -1 is -1. 3 plus -1 is 2. 2 times -1 is -2. Add those together, I get -6. Multiply by -1, I get 6. I have a remainder of -6. So once again, nope, that doesn't work. Let's try, again, I could try any of these. I like the smaller numbers, so I'm just going to try 2. 1, 3, -4, -12. Okay. Starting synthetic division. Bring down the 1. 1 times 2 is 2. Add those together, I get 5. 5 times 2 is 10. Add that together, I get 6. 6 times 2 is 12. Hey, look at that. The remainder is 0. So 2 is a root. But if I'm going to factor it, I need to write a binomial that would have a solution of 2. So I cannot put x plus 2 because if I set it equal to 0, that would give me a -2. I need to change the sign. So it's x minus 2 because once again, if I set it equal to 0, now I would get a +2. And then in my parentheses, I'm going to put my quotient. So that would be 1x squared plus 5x plus 6. We already have it to a quadratic, so I can go ahead and factor it using guess and check because a is 1. I ask myself, what factors of a +6, so I know I'm going to be using same signs here, okay, same signs, would give me a +5. So I'm going to have to put plus and plus 2 and 3. If the 6 were negative, you could have used the 1 and 6, but because it was positive, we had to use same signs. I just say that because I've seen a lot of mistakes with something like that. E had asked for us to factor the polynomial, which we did, and identify the x-intercepts, or our zeros, right? Zeros, x-intercepts, roots, they all mean the same thing. Solutions. They would be, in this case, set each equal to 0, a +2, a -2, and a -3. So when I was testing these, 2 was just the one that I found first. Had I tested a -2, my work here would have looked a little bit differently, or a -3, my work would have looked a little bit differently, but I would have ended up with the same solutions. Part F asks, are all of these x-intercepts we found on the list of our possible roots? So we ended up with a +2, a -2, and a -3. So let's look at our positive roots. Are these 3 numbers on that list? Yes. Plus or minus 2 is here, and then a -3 is right here. So I'm going to put yes. They were.